In this video, we'd like to talk a little bit about a tree graph and its redundancy. So this is an example of a tree. We have 1, 2, 3, 4, 5, 6 vertices, and there are 1, 2, 3, 4, 5 edges. There's a number of different ways that we can define a tree, and they all come back to the same thing. So a tree is a graph which has n vertices and exactly n minus 1 edges. So as we noted, we have 6 vertices but 5 edges. So if I had 10 vertices, I would have to have 9 edges. The graph has to be connected. If it's disconnected, then this relationship between edges and vertices does not matter. Another way of defining a tree is to say that every edge on a tree is a bridge. A bridge is an edge that if you remove it from the graph will become disconnected. So if I were to take away this edge right here between 4 and 5, then this graph would become disconnected. So, as an illustration, we could actually remove this edge right here. Erase it. And you can see that if I do that, this graph is now no longer connected. If I put the graph, the edge back, then the graph is connected again. And this would be true for any of these edges regardless of which one I removed. So if I remove this one, then this graph is not connected. If I remove this one, then I have this vertex out here which is all by itself, and the graph is disconnected. And so the same is true for every one. So this is another example of a tree. Another way of thinking about a tree is to say that there are no circuits in the graph. So a circuit would be two different paths to get from a point to the same point again. So if there was an edge here, let's say, then I could go from 4 to 3 to 5 back to 4 again. That would be a complete circuit. But there's no edge here, so if I go to 3, the only way to get back to 4 is to retrace this same edge. So these are our 3 different definitions for a tree. There are n vertices and n minus 1 edges. So however many vertices I have, there's one less edge in a connected graph. There are no circuits, or every edge is a bridge. Those are our 3 definitions. Now let's look at a graph which is connected but is not a tree. So this would be an example of a graph which is connected, but it is not a tree. So we can look at the 3 definitions. So the circuit is violated right here. There's another circuit which is violated right here. There's another circuit which is violated. I could go this way around back to 1. These are all, there's 3 circuits here. These are all violations of the tree rule. I could also count the vertices. I have 5 vertices, but I have 1, 2, 3, 4, 5, 6 edges. If this was a tree, I would have to have 4 edges, not 6. So this is too many edges. And I can disconnect one of these edges and the graph is still connected. So this is not a tree. Now, the number of edges that the graph has that I can delete until I get a tree is the redundancy. So essentially it's the excess number of edges. So let's delete some of these and see how many we get. So let's say I delete this one. Oops, wrong color. I delete this one. Well, the graph is still connected, but this is also still not a tree. So let's say I delete a second edge. Let's say I do this. Okay, so now this is a tree. Because if I start at 2, I can't get back to 2 without retracing my steps. So there's no more circuits in this graph. And if I count them, there's 5 vertices. There's now 1, 2, 3, 4 edges. That's the correct number of edges for a tree. And I had 6 before. I deleted 2. Now all of these edges are bridges. And so now this is a tree. So the redundancy is these number of edges that I deleted in order to make this a tree. Now let's start over again. Now, what if I deleted 2 different edges? Well, I could delete this edge and maybe this edge instead. So I deleted 2 edges and now I have a tree again, because now there's no way to get from 5 to any other, to back to 5 again without retracing my steps. And I deleted this, 2 different edges, but still 2 edges. So the redundancy of this graph is 2. So there's a nice simple formula for this. So it's the number of edges. So the number of edges minus the number of edges for a tree. So you can calculate the number of edges for the tree. Which, as we said, was the number of vertices minus 1. That's what you need to have in a tree. That would be this number. And then count the number of edges you actually have. So we'll make this edges actual. So the number of actual edges minus the number of edges you should have for a tree gives you the redundancy. So originally I had 6 edges. That's 6 actual. The number I need for a tree, 5 vertices minus 1, is 4, and therefore the redundancy is 6 minus 4, which is 2. 6 minus 4 equals 2. So the redundancy of this graph is 2.